Hello, good morning everyone, and welcome to SeptembRSE workshop on Flame GPU2. So it's really exciting because I've been running these workshops for some time with our older version of the software, Flame GPU1. This is the first time that we've actually managed to run a workshop on Flame GPU2, and it's been under development for a number of years now. So it's really exciting, but you are very much our guinea pigs as well. So please bear with us if there are any technical hiccups. Okay, right, so I'm going to share my screen. Let's hope Zoom doesn't do anything horrible. Okay, so do you see my slide? Someone give me a nod or a wave. Yeah, okay, I see a thumbs up from Kevin. Thank you. Okay, so let me just move this out of the way as well. Okay, so there's a few things we're going to do then in this workshop. So first of all, I'm going to give a talk, probably about 30 minutes or so, just to give you some context and background about Flame GPU. So really what I'm going to do is explain a couple of things about it. So I'm going to explain why Flame GPU, you know, how it's useful, why we have it, what the need for it is, what the architecture is, and give you some information on how to use it. And then I'm going to go over a bit quicker, some insight into how we did it, right? So it's what some of the challenges are from an RSE perspective. So that's probably more interesting if you're a practicing RSE, but it's also probably interesting if you're a modeler who's dabbled in kind of trying to increase the performance of an agent-based model. So after that, we've prepared a tutorial. So this runs within a Jupyter notebook. And we're going to kind of handhold and let you work through an example. There's a number of people in the room: Matt Leach, Rob Chisholm, Peter Haywood, who are part of the core development team, and we'll have an opportunity to go into little breakout rooms and have a bit of a discussion. I'd love to know what your interest is in Flame and find out a little bit more about any kind of modeling challenges that you have. My slides not moving on now. There we go. Okay, so the motivation then really for this and for the software is the study of complex systems. So a complex system is one where you've got emergent properties, and an agent-based modeling is really a method for specifying and simulating complex systems. So typically you're specifying the behavior of individuals, watching kind of emergent properties occur as a result of interactions within the system. And the simulation is really important because it helps us to understand that complex system. It can be used for things like interventions and prediction. The difficulty, of course, with studying and simulating a complex system is that it presents a computational challenge. So rather than the kind of the top-down equation-based way that's also quite typical, it means that you have to simulate all of these individuals. It presents a challenge in terms of compute and in terms of memory. And it's, yeah, this is really the thing that Flame GPU is designed to address. So it does that, and before I'll kind of go into some of the details, I want to show you some examples of some of the things we've done with it. So this is pedestrian modeling. You'll notice that the examples that I show you tend to come from kind of infrastructure simulation because they're quite visually appealing. Actually, one of the huge uses for Flame GPU is biological cell modeling. It's just not quite as interesting to look at kind of spheres moving around as people or cars. So the visuals tend to be kind of focused this way. The kind of the aim though is with Flame GPU is to abstract away all the complexities of parallelism. So create a simulator that is fast and efficient, but hide the details of how we do that with parallelism, so that a modeler can focus on modeling rather than on writing lots of kind of simulation code. So again, there's another example here that's come from simulation of vehicles. Both of these examples that you've seen are kind of looking at tens of thousands of agents interacting, which is pretty typical of what we can achieve with Flame, although we do have models running into the kind of the millions of agents. So the first question you probably ask then is, you know, is this a simple thing to do, right? So you've got a multi-agent system where you've got lots of independent agents moving around. Surely the performance can be improved just by throwing GPUs at it. You know, if you've got n GPU cores, will my multi-agent system run n times faster? Unfortunately, the answer is no. GPUs really, although they're a very powerful tool, they're not a magic solution, right? So despite the marketing hype where we see the potential for increases of thousands of times speed up, that's not really the reality. they're not magic. They're just a piece of silicon, just like a CPU. They're just a different architectural design. The architectural design differs because it places a lot more emphasis on raw compute performance, whereas a CPU has got lots more caches available, so it means that it's very good for tasks that are kind of high latency. GPUs are much better at things that are kind of high throughput. So it's kind of the difference between a motorbike and a bus, if you like. The difficulty with programming GPUs, though, is that because you're missing that kind of high latency and large amounts of cache, it becomes much more difficult to program them and to achieve the potential performance that you could get. So in order to use all of that, that raw processing power that's dedicated to compute, you need to be much more intelligent in the way that the GPU software is designed to make sure that you can keep all of that compute busy without kind of waiting on moving lots of memory backwards and forwards. And this is a difficult thing to do with an agent-based system because agent-based systems, despite the fact that agents are kind of individual, the whole problem of solving or simulating a complex system is not embarrassingly parallel, because agents do all kinds of annoying things like reproduce and die, and above all else, they communicate. And that communication typically is over restricted distances, whether it be across networks or spatial distances, all of which requires things like spatial data structures to be built, which is not an embarrassingly parallel problem. There are parallel ways to solve it, and that's what we do within Flame GPU, but we abstract that away. So as I said, this talk then is going to focus on two things, on the approach that we take and then some of the challenges. I'm going to move on to the first part and give you a description of Flame GPU then. So it's very much driven by this kind of methodology that we have of RSEs, of having better software and better research. There's a significant problem really with lots of agent-based models in that what people tend to do is maybe start their model in an agent-based modeling framework, which is kind of usually designed for the CPU, and frustrated by the level of performance that they get, people tend to then say, well, I can implement something better. So they take their model and then start to implement, create an implementation of that model in whatever language that they choose to try and gain some extra performance. But in doing so, they start to link the implementation and the model together, and they become intertwined. The problem with that is that if the model and implementation are intertwined, it becomes much more difficult to test the implementation and much more difficult to test the model. So it means that verification and testing becomes much more of a difficult process. And it can mean that it's much harder to understand whether the results can be trusted. This is particularly kind of topical with obviously the COVID modeling work, where we've seen obviously criticisms of some of the COVID modeling, and although that's been proved to be reproducible, that there are kind of claims that although it's reproducible, it's still quite horrible code to look at because of this intertwining of the model and the implementation altogether. Flame GPU very much wants to solve that in providing separate simulation software that is well tested and performant, and the ability to then describe a model which can be independently verified. So in order to do that, you really need to have a very good abstraction that allows modelers to have the flexibility that they would have without them kind of coming up against something that means that the framework is unable to support them. So we've got a very general framework and description for what an agent-based system looks like within Flame GPU. And the way we do that is by using a state-based representation of agents. So by having this state-based representation, effectively what you can do is describe the model in terms of what the agents are, which other agents they communicate with, what the information they hold is, and what information they communicate with others. And then you also describe the behavior, so what the behavior is when information is exchanged. And then also, because it's state-based, we have this nice ability to parallelize the model in a particular way. So the example that we have on the right of this slide is probably the simplest example of a Flame model that could exist. So it's a single agent denoted by the kind of the vertical line. The two circles are kind of represent like a state, if you like, and then the boxes, the square boxes represent functions. The green box represents a message. So within this model, all agents will implement the send locations function. The only purpose of that function is to communicate some information via a message. That message is stored in that green location message board. And the next agent function that they will perform is called move, at which point they will consume all of the messages, or perhaps a subset of those messages, and use that information to perform an update. So because there is a separation of those functions and we don't have any kind of direct agent interaction, it's all indirect via messages, we can have some assumptions that we can make about this model. So we can assume that the move function is unable to occur until all of the send location messages have been completed. That means that we have a synchronization barrier that prevents things like problems with implementing it in parallel effectively. Yeah. So from that very, very simple model, and this is a model that we use typically for benchmarking, we can observe emergent properties. So just by having agents output a location and then read all of their neighboring locations, move towards an area of effectively, sorry, this has got an attractive and a repulsive force which we can parameterize, and the result is that they form these kind of nice spherical formations which eventually kind of merge and combine as well. So whilst that's a very simple model, there are examples of models which are much more complicated. Now, obviously, this is a very complicated example, but by having that separation of model, it means that we don't have to worry about resolving kind of all the dependencies and potential race conditions that may occur with kind of functional and message dependencies. That's all handled behind the scenes with the framework, and we can simply visualize the model in this kind of nice graphical format. So with Flame GPU, we didn't start with Flame GPU 2, sorry, we didn't start from nothing. So Flame GPU has existed for some time. It's something I first started in my PhD work. And the way that it originally works was that you'd take the model description, you'd take the behavioral scripts, and the model description would be processed by a whole bunch of templates. So your model description would be expanded and templates would generate lots and lots of code, and that would then be turned into a finished simulation which you could compile and then run. This was really, really nice because it was really performant. It meant that you could generate a nice fast GPU code, you could hide the GPU code in the templates, but it meant from a research software engineering perspective, it was a nightmare. Because any change we had to make wasn't just made in nice code that we could run and compile and test. It was made within template files. And the only way to test the template files is to generate models. And because of the complexity of the template files, you might not generate code, you might not generate all examples of code that could be tested. So it was really, really difficult to write, really, really difficult to maintain, really, really difficult to test. So obviously we had to do something about that. And what we did was we came up with the Flame GPU 2 API. So instead of using templates, now what we do is we have some very clever C++. We still define models and behavioral scripts, but they're all now combined within a single API. So it's C++ based, but because things can now be defined at runtime without having to kind of use templates to generate code, it means that we can generate bindings for this C++. And that's exactly what we've done with Swig to generate PyFlame GPU. There is some exception to this that I'll kind of come across in a moment, but effectively it means that we can dynamically generate models, build them on the fly, and we don't have lots and lots of code repetition within templates. It's much more modern, much more maintainable, and we've got loads and loads of tests, which mean that we can have some confidence that at least our simulator is correct. So in terms of describing a model, then there's this kind of hierarchy of objects that exists. So there's a simulation. A simulation has both a population of agents and a model. So the population is dependent on the description of the model in terms of which variables it will have and so on. I'm going to quickly go through some basic syntax of describing a model. So this is covered in the tutorial part as well, but I wanted to go through it just briefly now. There are some extra bits that we're not going to kind of cover within the tutorial. but perhaps we can have a discussion about those maybe later if there's parts that people are interested in. So the first thing to do is obviously create a model. So by using the PyFlame GPU Python package, you can create a model. You give it some name. The name is not particularly important. From that model object, we can then start to add new things to the model. So to add an agent, it's just a case of creating a new agent. So model.new agent. Agents effectively have got a number of things. So they have variables. In this case, we say that our circle agent, so this is the example that we saw of the benchmark example that we saw in one of the earlier slides. We give it an ID. The ID is important because when it's iterating through messages, it doesn't want to read its own message and consider that as part of the information. It wants to kind of only consider its neighbors. So we give it an ID so it can perform that check. It has obviously an X, Y, and Z position. It has a drift variable, which is something which is used to store the distance that it's moved. So we use that for part of our validation of this particular model. And then it has a number of functions. So it has an output message function and a move function. The way that we specify a function is that we, at the moment within Python, we specify that as a Python string. So the thing that is contained within it is actually C++. It's not particularly scary, C++, and if you can program in Python, then there's absolutely nothing within the function description that you wouldn't be able to program. I'm going to show you some more examples of those in a moment. The other thing then is we need to define what a message is, what the information is that's communicated. So we define the message as being called location. And again, we're going to give it the same variables that the agent had. We don't need to communicate the drift variable. We only need to communicate positions and identifiers. So we define those variables to the message. There's different messages that we can create. And one of the abstractions that we use is to define, and we use messages, sorry, for kind of separating those. So message brute force effectively means that anyone that reads that type of message will read all of those messages. Spatial messaging means that you know, if you want to read messages only within a particular radius, then anything that reads that particular message will have to specify an initial position, and then it will return only, so the iterator effectively will only return messages within a particular distance. We have a number of other more specialized message types that allow you to do things like 1D, 2D arrays, so that's more like a cellular automata, and then buckets where you've got like a discrete grid which is containing certain things. It's also expanded into things like network messaging, which is like a specialist implementation of bucket. So the other thing that you might want to define within a model is environment variables. So these are variables that are read only by agents, can potentially be changed between iteration steps or perhaps parameterized as part of your model run. In the example that we have for the circles model, we have a repulsive and attractive force that is global across all agents. So it's a good so they're good variables to put as environment variables. So we define those using the model environment. And then the final thing we do is we have to define the execution order of the functions. So there are two functions. There's only a single agent, so there's only two functions that we need to worry about. We create a number of layers, and when we add the functions to the layers, it ensures the kind of the execution order and means that the move won't occur before output message is completed. So there is a slightly different way that you can do this via dependency analysis, where rather than explicitly defining the layers, what instead you can do is you can say move has got a dependency on the function output message, as well as having a dependency on reading the location message. And if you do it that way, it's just a slightly different way of defining it, but it means that this graph will be calculated for you. So in order to run a simulation, then you need to create a CUDA simulation. You pass in the model and then you initialize it with any arguments that you pass through to your particular script. So there are certain arguments that you can pass through that configure, say, which GPUs to use and things like that. They're all documented in our Flame GPU docs site. we create a population by creating something called an agent vector. Once you've got an agent vector, it defines what the agent type is. So in this case, it's a circle agent. And then we can iterate through that vector and set the variables of particular agents. So because this population is of type circle agent, we know that there is a variable called ID, X, Y, and Z. So obviously, if we tried to set a variable name for a population that didn't exist within the agent description, you would expect a runtime error, and that's exactly what you'd get. Once you have a population, we can set the CUDA simulation's population data, set the number of steps that we'd like to execute, and then call simulate. This will instantiate everything on the GPU, perform the simulation, and then, should we so wish, we can write the results to a file at the end. So this is a very simplistic view of it. There's much more complicated things you could do in terms of the way you log that data, the way you graph that data, and you'll see that in the tutorial where we kind of log population numbers over time. Similarly, there's the opportunity to do things like visualize, which we're not going to cover today because remote GPU visualization on cloud instances is a really difficult thing to do. So I mentioned agent functions need to be encoded as a Python string. So this is kind of what those look like. So this is C++ code, but this is compiled at runtime. So when you specify this within Python, it's compiled at runtime and linked against Flame GPU library, and so that it can be kind of executed when you call simulate. So here's a really simple example of a Flame GPU agent function then. This is our output message function. It uses this Flame GPU singleton to access the message out object, and then we can set particular variables. We can retrieve variables from a particular agent. Each function represents the function occurring on a single agent instance within the simulation. So when you say Flame GPU.get variable, it gets the unique variable associated with any particular agent within that population. There's a couple of arguments that go into this agent function. So there's the agent function name, there's the input message type. So obviously, and then the output message type. So for the output message function, there's obviously no input message type, so we use this message none. And then for the output message type, we've said that it will be brute force. It's a brute force message, so this needs to match with our model description. The final thing that our agent function does then is it returns a single variable which determines whether or not the agent continues to live after the execution of this function. So if it returns alive, it remains persistent. If it returns dead, then it will be removed from the simulation after the execution of this function. So another slightly more complicated example of an agent function then is the move function. So this is slightly more complicated because it does a number of things. So firstly, it gets agent variables just as you saw previously. So the top line is kind of getting the ID. It also gets from the environment the repulsive and, well, in fact, it just gets the repulsive force. Further down on a line, maybe about 10, we see that we have like a for-based range loop where we're kind of iterating over the message in. This allows us to kind of iterate over the messages. So these are the location messages that this move function is allowed to consume. It will get all of the variables from those messages. I've excluded the calculation for actually determining the force, but you can assume that there's some calculation in there that updates the fx, fy, fz variables, and then those are then used later on in the agent function to update each agent's individual x, y, and z positions. So that's pretty much it in terms of specifying an agent model and simulating one. As I said, there's some other kind of more complicated things that we've done behind the scenes that I'm not going to go into in this tutorial, but they are kind of documented within our kind of docs site. So I'm going to now briefly just cover what some of the challenges have been in implementing Flame GPU 2. So it goes beyond really just the kind of abstraction, but really touching upon this idea of kind of generalized versus specialized code. So when someone implements an agent-based model, say on the GPU or for any high performance reason, if they do so for a very specific model, they can probably achieve very good performance. But because we want to do something that generalizes for all kind of agent models, whether it be cells or people or vehicles, it's much more difficult to achieve that same level of performance. And that's one of the main challenges that we've kind of had to address. One of the kind of the really big problems. Oh, I'm sorry, my dog is barking. One of the really bigger problems that we've had is really the change in GPU architectures over time as well. Because when I first started writing Flame GPU, you know, we could simulate reasonably big models, you know, talking about thousands of agents, and that would be enough to keep a GPU busy. But since then, you know, GPU performance has improved considerably, but as has the level of kind of parallelism required. So since then, up to the A100 hardware that's available now, there's almost 14 times increase in the level of parallelism within a GPU, which presents a challenge, partly because, you know, agent models haven't necessarily scaled in the same way. So you now need potentially up to hundreds of thousands of individual threads to keep a GPU device busy. And that translates in Flame GPU to hundreds of thousands of kind of threads of execution, usually requiring hundreds of thousands of agents. And quite frankly, not all models need to be that large. So one of the ways that we've kind of made some improvements then is by making sure that if we have different types of agents within the simulator or within a particular model, sorry, then what can happen is they can be overlapped. So if we have, say, agent A and agent B, then it means that we can overlap that execution to keep a GPU busy. So you need lots and lots of threads to keep it busy. And in Flame GPU 1, we couldn't overlap those two things at once, so that it would kind of be sequential. Agent A would implement, agent B would implement. So what we can do within our graphs is where we have these overlapping areas and overlapping functions, we can now have these overlap and hopefully achieve better utilization of the device. That's exactly what we've done, and we have a benchmark of something called a concurrent Boyd's model. So this is very similar to the circles model, but it adds the traditional kind of Reynolds-Boyd's behavior so that we get nice flocking. And what we do is we add lots of non-interacting species, and hopefully what we should see is not a linear speed up, because you would expect it to tail off as the GPU device becomes saturated, but we should at least see that particularly for smaller models, we're able to utilize the device better. So we kind of see that. It's not perfect, and this is very much in the theme of the talks at the beginning of the conference. We wanted to share our code, the good and the bad, and this is unfortunately partly bad because it's not as good as we hoped. But we understand why, and there are areas that we can certainly improve upon this. I'm going to skip over this slide because it's much of the same, just with slightly bigger population sizes. So another challenge that we've had to address, and one of the other things that helps with big GPUs is stochasticity. So when someone runs an agent-based model, typically they don't want to run it once. They want to run it a number of times, because even under the same conditions with a slightly different seed, you can get very different results. And here's an example of just some crowd behavior where agents are just trying to cross paths, where we see that one of them gets stuck for quite a large amount of time. And they're both with exactly the same starting conditions and slightly different, but just slightly different seeds. And this is something that we've had to address with some of the modeling that we've been doing recently. So we've been doing some COVID simulation, not epidemiology, but simulating pedestrian movements around the train platform interface. So this is work that's been supported by RSSB and UKRI. And this is typically quite small models. So we know that we need hundreds of thousands of threads to keep the GPU busy. But with small models of less than 1,000 people, we do know that we need to parameterize those to find conditions which are favorable, and also to make sure we run enough simulations of the same thing on the different seeds to prove that they're kind of statistically significant. So we typically have many more than 1,000 simulations to run at once. So we've benchmarked that then, and the thing that we call that in Flame GPU is an ensemble. So you can specify a model, a simulation, and then you can create an ensemble of that simulation to run it lots and lots of times. And we see that we do get some effective speed up. There's a sweet spot because if the model is far too small, then it's difficult to utilize the device because there are some restrictions on the number of things that can happen at once. And if the population is very large, it's going to kind of keep the GPU busy anyway, and that's going to kind of serialize the ensemble. But generally, it's better to oversubscribe a device with something like an ensemble rather than lots of separate simulation runs. In terms of our general model scaling performance, it's pretty good. These graphs are mostly meaningless, and I fully acknowledge that because it's completely dependent on the model in terms of the performance that you get. So this is only really useful if you're interested in the specific circles benchmark model. Even changing the parameters of the model will affect the performance, because if you interact over a larger area, it means that there's more messages to consume, and the performance will change possibly quite drastically. But in this particular example, there's one agent per unit of volume and an interaction radius of 2, which means over time there's roughly about 200 interactions or 200 messages read per agent over the kind of the 200 iterations that it runs for. So it means that we can do, with our fastest implementation, which is using spatial messages rather than brute force for this model, we can do about 20 simulation steps per second for about 1 million agents, which is pretty good. The other thing to consider then is, how big can we go? And this isn't limited by performance. This is typically limited by memory. So once you get up to a certain point, once you get over, say, 200,000 agents, then your performance is effectively going to grow linearly, because once the GPU is fully saturated, it's just going to kind of sequentialize the execution of each of the agents. But it's still going to be very efficient, so it can be highly advantageous to run simulations of 1 million, 2 million agents on a single GPU device. So we kind of estimate that with the circles model, we can probably go up to about 5 million or 500 million agents, but we've never had the need to do so at this point. Although there are some biological models that we're coming across now that need in the order of 20 million agents. So in terms of what's next, well, we have some big EU projects in which Flame GPU is being applied. So in particular, the simulation of neuroblastoma. So this is ambitious in that it wants to simulate a whole tumor scale simulation. So that's 10 million to 1 billion agents. Although that's not contained within a single model, that's done using patches, and we use a multi-scale approach. There is a need to run a large number of patches, typically with around about 2 million agents each. And then the multi-scale approach does some harmonization between those two things. The other area is immune system modeling for TB vaccinations. We also have obviously an ambitious list of development activities that we'd like to undertake in terms of adding some multi-core CPU support for kind of falling back for systems that don't have GPUs, or for perhaps for agent populations that are so small that the GPU would be ineffective at speeding them up. So just to kind of conclude then, GPUs can be applied to accelerate agent-based systems, but doing so for the general case is hard. So Flame GPU kind of builds upon like a decade experience of simulating agent-based systems and applying GPUs also to simulate things very quickly. So it gives you kind of flexibility without losing performance. It gives you very high performance for increasingly small models. So it addresses that kind of big GPU problem. We've got these nice Python bindings now, which we hope will open up the software to a much broader audience. The software is completely open source. It's kind of a nice example of some of the best practice that we apply within the RSE group at Sheffield. It's not perfect. There's always room for improvement, and we're happy for people to raise issues and give us contributions and advice. If you're interested in the software, then just get in touch with me. And I think we'll move over this point onto kind of trying out the tutorial exercise. So there's two ways that you can do this, and I'll kind of get people started off with that, and then I'll kind of open up for questions. But there's two ways to do this. So one is to go to a site called instancehub.com. So this is something that I've written for handing out GPU instances. So I use this for teaching GPUs and running tutorials and things. If you register at that website with the email address that you use to register for this session, then you will be able to, and in fact, I'll give you a demonstration of it in a moment, kind of give yourself a GPU instance and it will all kind of load up nicely for you. Alternatively, you can use Google Colab. So if you go to the Flame GPU homepage, there is now a link at the top of that says try in Colab, and you can click that and it will open you a Colab notebook with the tutorial kind of ready loaded. Just need to make sure you change the runtime to a GPU backend. Obviously, it won't run on a CPU. Okay, so thank you very much, everyone, for listening. Does anybody have any questions at this point? Of course, I can't see if people have got hands raised because I'm still sharing my screen. There we go, yes. Okay, so I can't see any hands raised at the moment. So if I'd suggest then that people go ahead and try. So Kim, you've got a question. Do you want to ask it now, or do you want to wait till you're speaking to one of us separately?
I just want to know what the difference between those two options is, the Instance Hub or the Colab.
Absolutely none. Colab is some free GPUs that Google hand out, but they are limited. So if you've used them quite heavily, you might not get one. They're also they're not great GPUs. They're fine for doing this tutorial exercise, they'll work, but they're not particularly performant. Instance Hub uses some slightly better GPUs that are provided by AWS rather than Google, and I pay for them rather than them being free. Yeah, but the Python notebook's exactly the same regardless. Okay, so I'm just going to very quickly show you on Instance Hub. If you log in using the account that I said, then if you click on View My Labs, you won't get a list of labs like me. You'll just get one that will say it's live. And if you click Participate, no, it won't because I've used up all my sessions. Right, okay, ignore what I'm doing for a moment. Right, okay, we'll try that again. Okay, so if you go on View My Labs, you will see that you have something that says Participate. When you click Participate, you click the Start Lab button, some stuff will happen in the background, and in about 2 minutes' time, this connection information box will fill in with login information, including username and password. If you click on the tutorial notebook link, once this has got to the end, you'll then be able to log in with with the password that's provided. And it will just open the notebook and you can go from there. Okay, right, I'm going to stop sharing my screen if I can find the button. There we go. And I'm going to stop the recording at this point now as well.